So hello, everyone. I'm really happy to see all of you here. My name is Oleg Šelajev, and I come from the room number 1 from the previous session. So if you saw me there, I can repeat the first slide for the people who didn't see me there. So my name is Oleg Šelajev. We are going to talk here about creating programming languages, which is the absolutely dream of any software developer, almost any software developer, just to create the actual language that they will like and use, and other people will like and use. And we do that all of the time, even like professionally or less professionally. So we'll talk about what options you have for creating languages on the JVM, managed languages, and we'll create actually a tiny language. So spoiler alert, that would be the calculator. So if you expect something esoteric and complex, we won't go there. But I will give you pointers, pun intended, to where to look forward and what to see next. So I come from Estonia, and I work at a company called Zero Turnaround, where I am a developer advocate. So that means my main responsibility is to care about the community and try to give back to the developers all over the world some part of the knowledge that I acquire or have by working in the Zero Turnaround products before. So I maintain the corporate blog called Rebel Labs, where we publish technical content for developers. I'm a co-lead of the Virtual Jug, which is an online-only Java user group, which is amazing because first we have access to the best speakers, and we can invite them, and they don't actually have to fly, and we can get the best content out of that. And it's easy for regular developers and attendees as well, because you can actually enjoy a really great session out of your home, like being in a bath or something. So if you're not a part of that activity yet, so just Google Virtual Jug and join. This is absolutely terrific. So if you have any questions or if you want to continue discussion, find me on Twitter. This is one of the highest interrupts that I have, and talk to me. I'd be happy to respond. So the Zero Turnaround is a company that does tools for Java developers. Currently, we have 2 main options that you can have. JRebel, which is a productivity agent that allows you to reload the code in a running JVM without restarts, making your development process kind of speedier and swifter and making you happier. And XRebel is the performance tool for Java developers for web applications. So those are amazing. People love it. If you look into that, my employer will be happy, and well, they will make me happy and send me to other conferences to talk to people. Without further ado, let's talk programming languages. And when we talk about programming languages, you have to understand that, and we all have to understand that, this is not a new subject, right? There are hundreds, literally, of programming languages developed in the last 60 years now, 70, and they have all kinds of shapes and properties, and they change, and every time a year passes or not, people create a new programming language, and they say, oh, now this is the hip, this is what we achieved, this is really how we should do programming languages. And currently, for example, for myself, 2 languages that I'm really interested in one is Elm, which is the functional programming languages for web, kind of really cool, and one is PonyLang. So who knows PonyLang? PonyLang is an amazing language, and they have the best documentation and very cute logo mascot, an actual pony. So if you are into programming languages, those 2 is what I recommend you to look at. They're not on the JVM, but they make very interesting design choices. So I hope you are all into programming languages, because you are all here. So that would be a nice thing to do. But the thing is, why cannot we create an ultimate programming language and just decide that, OK, this is a solved problem, and we don't want to spend any more time on creating the killer of Java or a better Java or something and just say, OK, Java has its quirks, but, well, this is what we got. This is the ultimate thing that we have, and let's stuck with it. So the answer to that is that, well, languages are tools. And like any tools, there are certain tasks that are better to be solved by a hammer. Certain tasks are better to be solved by a saw. And some things require a screwdriver. So in the same way, like we can have general purpose programming languages where we can have DSLs, or we can have esoteric languages. We can try to optimize the developer's time when developing applications and do something like Python, which is easy to teach to people, and kind of it's really fast in development. Prototyping is good, but then maybe the execution is not as precise and fast as on something on a different problem. And there are all those many choices about flexibility. How does it work with the previous libraries that we have accumulated for, well, on the JVM for 20 years now? And how we will maintain that, and we will break everything again and again with every release, or we will maintain any sort of backward compatibility, consistency between the behavior. Do we want to create the most terrible Malborge-like programming language that you would absolutely have no chance to write any sensible program in? Or there are different purposes why we create languages, and obviously the trade-offs of that for that are different, and solutions how you decide should you go with this decision on that. So one of the cool languages, programming languages that I know of is Piet. And Piet is a programming language where programs look like abstract paintings, like that thing on the right of the slide. That is a Piet program. And it encodes the instructions in this shape. And the author of that language wanted to call it Mondrian, but that name was taken with another programming language, which shows you that actually it's really hard to stumble on a new idea in the space of programming languages, and we kind of reiterate and trying to pick the best parts of different things. But the thing is, the comment that struck with me is that we can't all be esoteric language writers. And this says the man who created this. And obviously he did that for fun. Obviously nobody creates financial systems using Piet. It's a toy language. So on this talk, I would like to concentrate on creating kind of very tiny, kind of complete, but tiny languages, and tell you about the options, what you have when you want to create that. So if you write programming languages for a living, right? If you were a Scala core committer, or you contribute to OpenJDK every day, this talk might be a little bit underwhelming for you. If you want to create something really cool looking and say, I claim this, nobody before me has done that before, this is the talk for us. Is that a video or a picture? Sorry. So I recently stumbled, not recently, somewhere in winter, I stumbled on a collection of blog posts by Jakub Dziworski. I probably butchered the surname. Jakub, are you here? I know that you're from Poland. I hope you came to the Jakub? No? No, Jakub. He's a great developer. He maintains a blog. And basically what he did, he created a series of 20 blog posts explaining creation of a language on the JVM from the very beginning to adding more and more features to actually writing a more or less complex program that dealt cards and something in that language. And well, Jakub, if you would be here, I would buy you a beverage of your choice. But unfortunately, really wanted to meet you. So if you consume the written content better, that is one place on the link that you could go and check how step-by-step you can build a language and add features on top of that. Essentially, to build a language, you will need to build several parts of that. So any language is a tool chain. It's not just, well, you can look at that as a monolithic system, but there are different parts of the system that do different things. And essentially, you will need at least 3 modules to design a programming language. You will need, because, well, you specify your program as a code, as text, and at the end you want something to actually execute and flash different color pixels at you or write some text. So you need to transform this into that. So the first step, you will need a lexer, which takes the code, the text, and produces you tokens of things. Then you will need the parser that takes those tokens and creates some kind of representation of the program that you have. Usually those are the abstract syntax tree, and we'll look into a little bit further into how to do that. And then you will need a compiler. And a compiler basically is the thing, who knows exactly what a compiler is? It's a translator between different languages. It takes program in one language and outputs the program in a different language, or in the same language, but a different program, kind of more optimized, hopefully, or something. So basically, it takes a program. It's a program that works on programs. Its input is a program, and its output is a program. So we will need a compiler that will take the abstract syntax tree, this form, some representation of our program, and it will produce some kind of executable code. For example, the machine code, if you're into assembly. Or, for example, Java source code, if you're into Xtext, or JVM bytecode. And then you will get to leverage the existing platform. Will it be the operating system executing your machine code, or will it be the JVM executing your bytecode, or any kind of platform? So to create a language, you will need those 3 components, or a series of it. So let's go really quickly through that. So lexing is a very simple pre-processing step. What it takes text, and it produces you a stream of tokens. So why it does that, it simplifies the reasoning about what actually is written in the program. And lexing is a simple problem. You create a finite automaton, and you say where the identifier starts and where the identifier ends, and what expressions can go near each other. And you feed that into lexer, and then you get that. And many problems, surprisingly, many problems can be solved by lexing alone. So not in just programming languages design, but in general. Because lexing is a finite automaton, and that is what regular expressions are. And we all know that you can solve almost any problem with regular expressions. They just tend to grow. So now we will have this stream of tokens, and we will need to parse them. And parsing is where the semantics of your language is happening. So you see a plus sign, and you know that this is an operation, and that this is a binary operation, for example, and it can take, well, numbers, or it can take strings, or it can take expressions. And you transform the stream of data of those tokens that lexer provided you, and you create the first representation of the program that can be executed. So when you have an abstract syntax tree, you can just walk the tree and interpret the commands. So you say, the example here, you see, OK, we have a plus operation. Let's go to the left branch and evaluate that. And then let's go to the right branch, evaluate that, and add those values together. And this would be an interpreter, and this would be a working example of a language, though somehow not very rewarding. So it's more like a prototype of the language. We would really like to build a compiler, because compilers are real stuff, the programs that operates on programs, the meta programs. And the compiler is essentially anything. And it's the most valuable thing in this tool chain, because it can actually execute and transform your program and explain your program to the machine, to the computer. And in a nutshell, you would what you typically would do, you would have a chain of compilers, and they will crunch your program a little bit and modify the structure. Maybe they will remove the unnecessary nodes from the AST. Maybe they will convert the abstract syntax tree in some sort into a different sort of internal representation of the program semantics. And you will pass that through this chain of compiler unicorns, and they will do all their small things and add optimizations and generate the actual code and so forth. So the compilers are the most interesting part of creating the language. And there are tons of resources for compiler writers. There are books, there are everything. I really like that internet page that goes through a ton of resources. There are 100 links on that page through philosophy or how to build a compiler, how to do optimizations, what is a SSA is single state assignment or something, and how to do register allocation to be efficient, and how to generate machine-specific codes. And if you want to write a compiler from scratch, I would recommend maybe starting from that. But if you want to create your own language, and imagine now that we want to create the language and we want to get some recognition out of that. So not just for purely academic purposes of proving to yourself that you can create a language, but you want other people to look at that and say, oh, that is neat. So, and it goes like that, typically, in the modern world. You create a language, and you specify the semantics, and you create a prototype. And then you create this platform to execute programs written in that language. So when Google started the GoLang, they had to specify the semantics, then had to provide the runtime for that. They had to do things. When the PyPy Foundation wanted to create the just-in-time compiled version of the Python, they would need to do things and to create a low-level VM that works on a low-level representation of that. And then people start using the language. And the first thing they complain about will be the performance, that this language is slow. Anyone can write a slow language. That is not a great feat. We would like to write a fast language. So what we do, we say, OK, we will create a virtual machine, and we will write a just-in-time compiler, and we will profile the code, and we'll do things in that, and we'll improve the garbage collection. And this process is complicated. And it's incredibly complicated. And it shouldn't be that way. So essentially, what we would like to do, we would like to be able to specify the semantics and the parser of our language in Java, and then, boom, done. So we want to leverage the whole power of the JVM to make our language nice and fast and pretty. So we would like it to integrate with the existing libraries and stuff. We would like it to run on top of the JVM. We would like to have some interoperability between the native Java code and our language code, managed language code. And we would love to have the support of the tools. Like, how cool would it be to have the debugger for the language available out of the box? Who knows, or who has an idea how to implement a debugger for a language? Who is not listening? Okay, I don't know how to implement a debugger myself. This is something that I thought about this morning. I was just really frustrated that I couldn't come up with any decent idea how to do that. But we would like to do this in the remaining half an hour. Half an hour. Or until they kick me out of stage. So we will start from the beginning. We will have to create the lexer and the parser, and there is this great library called a tool called Antilar, and its current version is version 4.5 something, so it's quite mature. And what it does, it allows you to specify the grammar for a language, and it will crunch that grammar, and it will produce you with the lexer, which will take the source code and provide you with tokens, and the ability to create a parser for that stream of tokens. So it will take this kind of complex and cumbersome problem of transforming just like a wall of text into something that you can reason about and just make it not a problem. How cool is that? The book is probably the best reference into using that, but I'm sure you can get with just, if you want to get into that, you can get by just Googling quickly. There is a couple of really nice blog posts on the Jakub's blog, which I really enjoyed, about AntlerR and its properties. So how it works? It will require you to define a grammar in terms of what data structures you operate on and your program consists of, and what operations are legal within the source of your program. So, and the grammar looks like something like this piece of text, and well, you specify what it currently says here is that we'll have a program which is one or more expressions, 0 or more expressions. And an expression is either 2 expressions separated by a star or a slash, or 2 expressions separated by a plus or minus, or expression could be an integer, or it could be an expression in parentheses. And we specify other tokens that we used, so that the int is just a number of digits, and a new line is a new line. So basically, you specify the tokens that are legal in your language. So for us here in this expression, in this example, the token would be, the main token that is legal would be an expression that can be of multiple types, but still, expressions are combined of other expressions down till the numbers. And if we feed this grammar to UntitledR, then it will generate a bunch of Java classes, and it will allow us to compile those Java classes, and it will allow us to execute this like graphical user interface thingy and feed it a piece of source text. So if we provide this expression 100 plus 2 times 34, which is a legal expression in our language, in our calculator, right? It will parse it and will provide us with a tree like you see on the image. And this is sample, and we'll go into the code just in a minute. This is where the interesting part starts. So the lexing is really easy, but now we need to interpret that parsed tree of tokens. And this is where all the interesting things happen. Well, we need to determine and say that we'll have variables or we'll have the functions, and the functions will work according to the semantics, and they will see things in the global context, or they will not see things in the global context. And we will say that, oh, you know what? We have this keyword this, which in some languages refers to this object, but in other languages like JavaScript, it refers to, I'm not sure, whatever, it can refer to anything. And we will need to figure out that when we will want to have functions in our language, right? Because this is the essential building block of language. It would be really sad, a language without functions. We will need to say that when a function is executing itself, it has access to local variables, and it has this chunk of memory for the current frame on the stack. And then before that, there will be a different frame on the stack. So if our function returns, we want to get back to that point of time. And this is kind of not that easy. If you consider, for example, how to implement functions and calling functions on the AST, through the AST, and how to interpret that. That is not very easy. And then we would like to have a type system, right? Who likes dynamic languages more than static? Who likes static languages more than dynamic? Good. I like static languages myself more as well. Dynamic are fine. I love Clojure, for the record. Clojure is a great language. But static feels kind of closer to heart. So, and we would like the the interpretation of that tree or of our program to be actually efficient. And maybe we want to have the garbage collection because we would like to allocate objects and don't think about that. We will need this runtime, and we'll need to connect the concepts from our language to that concepts of the runtime. So imagine we sit on the JVM, as we do, and we'll have those like method stack frames, right? And we would like to map the functions that we have in the language to those, and we would like to use the primitive types from the JVM because we know that would be more efficient, or maybe we don't want to do that. But there are a number of problems that it just works through connecting the concepts from the language to concepts on the platform. And those are hard problems. And solving hard problems is really, really, really expensive. And it's only cheap in one case. Solving hard problems is cheap when somebody else paid for that before. And they allow you to use their things. So welcome the Johann Kepler University and the OpenJDK. They have two magnificent projects in the current branch. So they have the Graal, which is the dynamic compiler and an interpreter for a language runtime. So basically, Graal is a compiler for Java and the code in Java written in Java. So if you are into compilers, but you're not into pointers and you don't want to go into C, Graal is the perfect opportunity for you to touch and tinker with a compiler written in Java. And then there is this glorious unicorn of our talk today, is a Truffle, which is the managed language implementation framework on top of the JVM. So as a framework, it will provide us with many things that would be really hard to implement from scratch and give it to us for free, or for a couple of Google searches and sleepless nights. So essentially, Graal is a very optimization-oriented compiler. It's very modular. It's designed to work well on the JVM. It is actually functional in a sense that works. There is a Graal VM, which is a JVM, and it works like a JVM on several hardware platforms. Not sure that all the JVM platforms support it, but on several definitely, like x86 is definitely something that is supported, or 64, normal processor, not ARMs. So, and it's a compiler. And Truffle is an even more interesting beast. So what it does, it tries to be really efficient in mapping and giving access. So Graal wants to compile code. It wants to compile the language to make it super efficient. So Truffle will be the bridge between the Graal or between the VM and the language. So it will have all kind of cool things that it can do for you, including the creating a very efficient code. And it will be the central piece between those things. So Truffle is a framework for managed runtime languages. JavaScript runs on Truffle. JRuby, it is possible to run JavaScript through Truffle on Graal VM. It is possible to run JRuby on Truffle through Graal VM. It will be possible to run your language through Truffle on Graal VM or on Hotspot. And there are really nice tools for that. And like the debugger support or something else was there. Modular structure and type systems and everything. So this is where we go from the presenting mode to the code. That is Pitbull. If you, wait, that was the Pitbull. With words, let's not talk about it, let's do it. And with that, what I need to do, I need to make the displays mirrored, like that. Can you see that? So, and then we will go into the IDE, which is currently Eclipse Neon. And let's see if it zooms. It zooms. Magnificent. Please don't crash on me. That would be ridiculous. So we start our language implementation from the grammar, right? So we will need to describe to Untitled what our language consists of. And this is a very tiny example of a language. So what we will build a calculator. A calculator will be able to understand parentheses. It will understand the binary multiplication, division, addition, subtraction. It will not understand this individual minus or plus before the number unary operations. And it will work on numbers, which can be integers, or which potentially can have this dot inside of them, followed by some numbers. So they can be doubles, which are floating. And this is one of the cool things that we will do. You cannot see here. I don't know why this is not zooming, but I would appreciate if that would be zoomed as well. There are 20 classes right here. And when we have this grammar and we execute the operation on that grammar that says Untitled in the command line, Untitled math G4, it just spits 4 Java classes for us. So it gives us the math lexer, which is a functional class with all the information. What it gives us all the names for the symbols. This is one thing that we will use from the lexer. We'll use the names of the symbols to map the tokens to actually the semantic meaning of what is a plus. So we can say that, oh, when we say a plus, we want to add the numbers. It gives us a parser, which is also generated code, and it doesn't look that bad, but the only thing that we will use this parser from in a snippet of code that we copy-pasted from Stack Overflow about how to use Untitled parser. And it gives us a listener, which is the concept. The Untitled parser will provide us with a parse tree, which means that it is a tree of all the tokens in a way that they were encountered in your program. So in the same way as we saw this tree of expressions, we will have that. So if we look at the main code, the main class, we will start seeing some truffle bindings and some truffle code. Can you see that? I might go a little bit larger with font. So the truffle. Now you're wondering, how do I get this truffle? And it seems like such a low-level thing. And worry not. You just create your Maven project, and you just say, as a Java developer, I want to be able to specify my dependencies and have somebody else to go to the internet and download the corresponding jar files and bring it to me and put into a location where I can use them. Surprisingly, that is Maven, or Gradle for you. So we just say that we want the Truffle API, and we will want the Truffle DSL processor, and we will want the Untitled 4 runtime to be able to use Untitled 4 classes when we actually parse the tree. And with all that dependencies ready, the POM is very simple, so there are no like kind of sketchy phases or goals here. It's just straightforward Maven project goals execution. So Maven clean install will solve all the inconsistencies. What it does, what Truffle does for you, it actually generates quite a bit of code to help you. So you will need the annotation processing, but that comes with this Maven tasks by default. At least it came for this project for me. So let's look how we do. We ensure that we have the Truffle runtime, and then we create something called Polyglot Engine. And the Polyglot Engine will contain all the languages. It's a Truffle object. Will contain all the languages that Truffle currently knows of. So, and we would take a language by MIME type, and we will create a source object from a string. So say we will have a string coming from the standard input. we will create a source object from that standard input. And this is the code that I haven't changed. This is just saying that, oh, our source is in that language. And then we take this Polyglot Engine and we say, please evaluate this program for me. So at this point in time, we have this cloud of Untitled grammar and classes somewhere here. And in the main entry point into our program, it's a Java program, what we have the Truffle framework that creates the engine for us that will somehow obtain the description of our language, and it will be able to execute the programs written in that language. So how to do that? You have to declare a class. Typically it extends the Truffle language. And if you want to learn more about Truffle, the best place to start is, well, obviously Google Truffle tutorials and everything, but what they point into the Java doc of the Truffle itself. And the main entrance to that is the Truffle language class. So you go into that, and you declare that we want to register our language within the Truffle. And we say that this will be our tag. So pretty straightforward. So if we look at the language and what it has the context. So it is the execution context of the particular program in that language. So this is where your global variables will go, or this is where your global function definitions will go, or this is where your native library linking parts will go, or this is how you find what other languages available on the same Truffle JVM, on the same JVM running Truffle, and maybe you want to call your JRuby code from your JavaScript code, or vice versa. And you can do that through Truffle, because every language registers the context, and you can easily manipulate that programmatically. So we have the language. We will need to declare the Jmm Lang types, and we'll have two types, long and big decimal. Because our semantics of the language allowed us to have a dot inside the number, we will represent the floating point number with big decimal, because why not? And non-floating point with lowercase long, because we know the primitives are efficient. So we have the language that evaluates, we have the language defined and registered in the Truffle, and now we will have to look at the parse method. So when the language the engine executes on a piece of source code, we will need to parse that source into the number of Truffle AST nodes. So Truffle offers you the ability to create an AST, abstract syntax tree, using the Truffle notation and Truffle objects, and then with that AST, Truffle can go and execute that AST very efficiently, and it can bind that and use the whole power of the JVM underneath to execute that AST efficiently. So it takes care of all of very many hard choices that you would need to make when you're writing a language. So it gives you the garbage collection for free. It gives you the type manipulation basically for free. It gives you the function calling and efficient manipulation of like polymorphisms and everything essentially for free. What it requires you to do is to define your abstract syntax tree in terms of its objects, which is a very small price to pay for that. So when you get a source, what we do, we just create a root node, and this is where we go into describing the Truffles, we're describing our AST through the Truffle objects. So we just all goes through Java code. You just slap a couple of annotations on your objects, and that is basically it. The main method that you should pay attention to is the execute method on the node, and the execute will take the virtual frame object for you, and this virtual frame is actually the frame on the call stack. So Truffle does that for you, and it says, oh, it seems that you want to execute this expression and this root node, may I create this space for you to store your local variables and stuff? And it gives it to you. And you just need to use that. So obviously, in this example, we just completely ignore that and just say, you know what? We will, since the root of the application of our calculator does nothing, we'll go straight into the expression that we parsed, and we execute it generically. So this execute generic is very interesting. So all our nodes will be expression nodes because we are a calculator, remember? So there will be two different types, one node per operation. There will be the parenthesis node, and there will be numbered nodes. So the expression nodes will make use of JVM Lang types. So our expression will, by default, by virtue of this annotation, will know that it can hold long types, types of like long primitives or big decimals. And after that, we just either execute the generic, meaning that we don't know anything about the particular types of the operands for this expression, or we can execute long, meaning that we execute this piece of code before, and we expect that the operands are longs, and we can go into this much less expensive mode of calculating on primitives. So, and if we look at the, this doesn't zoom as well. So if we look at the implementation of that expression nodes, there are just parents, big decimal, and binary nodes for the operations. So let's look at the constant node. This is very easy. This is just the node that holds a value, right? So this is our number. This is the leaves of our abstract syntax tree where we actually will operate on something. And we have two of those. We have big decimal node, and we have the long node. And the only difference is that one holds the long value, and the other holds the big decimal. And they have the execute generic that just return the same object. So now the binary node is nothing more than an abstract class that says to Truffle that, oh, look, my node will have this many children, and I will call them left node and right node. And we need those annotations because when we specify the actual class, so the add node, for example, we extend that binary. So Truffle knows that we will have two children, and it will generate supporting classes for this type of node for us. Now this is where specialization comes in. This is really cool. So what we do, we provide the implementations to work on our types using the typical Java overloading rules. So we have an add method that has two long operands, and we use the exact calculation. We use exact instead of just adding two instances because we want to be sure about the overflow. So this add exact will throw an arithmetic exception if our two operands will overflow together, right? And Truffle will know that now I cannot do this computation with longs because this operation doesn't succeed, and it will go into a higher into a second language type that it will try. So first, our type declared that first we'll try longs, and then in the like left to right order we'll try big decimals, and you can have like strings and booleans here, and small booleans, large booleans, and so forth. So this addition, this thing, specialization is really cool. So Truffle gives us the ability to, from the beginning, to give it hints that, oh, this part of code you can execute very efficiently. And this comes in hand with this our idea that when we create a language, it will be fast from out of the box, not after several years when we actually come to implement that. So we have the specialization for big decimals, and we have the specialization for adding just two objects, because if we will have a long and big decimal, two operands, we will need to combine them. And we cannot cast from long to big decimal, so we'll need to provide this casting and conversion of the types manually. But figuring out which add to call is not our deal. It's not our problem. It's what Truffle does for us. In the same way, we have all the mathematical operations specified. So division is interesting because when we divide two longs, we can throw an arithmetic exception, and we'll have an overflow, and it will rewrite something on that. Multiplication and subtraction is also easy. So parenthesis as a node also doesn't have much. It just says, oh, actually, I'm a node that contains a different expression within me. So when we evaluate the expression within it, we just say like, oh, child expression evaluate. So now this is all cool. What we have to do now, we have to transform this anti-LR classes somewhere here, flying in this kind of cloudy thing, and convert that to this Truffle's AST implementation that we just described with those classes. And then we'll have the full picture together. What we do is that we have a listener, a tree listener. So what we'll have, we will traverse this parse tree of our created from our program source, and we will just convert that one by one, every node explicitly into the corresponding truffle nodes. So for example, when we will, so imagine, who doesn't know how the tree traversal works? So you go down to the left, and then you go right, and this is like left-right root traversal behavior. So for example, when we exit the number node, we know that this expression is a number, and we create this new either long or big decimal node on a stack. When we have the binary expression, when we leave the binary expression, so we looked at the left part, we look at the right part, and we are exiting through this expression, we just need to pop two operands from the stack that we are keeping while traversing this, and add the new node corresponding to the operation in the code. So this is where the mass lexer generated by Untitled comes handy, because it provides us with all the tokens that we can see. So we have 4 operations, and we just create this switch statement. And when we exit this binary node, we also push it on the stack so we can recurse into more binary nodes and binary nodes. And that is it, because when we do the eval, wait, not the eval. This is where we go, yeah, into the parse source method, where we take the source of the program and we parse it into the expressions, which is the Truffle AST, which we will call, we will execute the call target, meaning that we will create a function, and we'll say, Truffle, please execute this function for us, and here's the AST for you. And magically, the compiler will work for that. So here is all the Untitled code that you need to know. So you take the input stream, and you feed it to the lexer, and then you feed it to the tokenizer, and then you feed it to the parser, and from the parser, you get this prog context, and it's called prog because our program initially on the top level is prog. So we get this context, and it's a tree. It's a parse tree. And with a tree, we know we can walk through the tree. So we create a walker, and we create the listener, which will get notified when we traverse the parse tree, and which will be called when we exit or enter nodes. And this listener will create the Truffle AST for us on this language. So now we have this object, and we will say, Truffle, please call, and this is it. So what we saw in those 20 classes, there are 4 generated Untitled classes which will be generated for you, which will take care of going from source into the parse tree, which you can further transform into something closer. On the other hand, you will have everything covered by Truffle. So you just need to call the API in the correct way, and you will need to specify the AST nodes in terms Truffle understands. And now the only thing that you are required to do to build a successful, pretty fast language on top of the JVM is to specify the semantics of the tokens in your parse tree and map them into the Java objects that you created for the AST for Truffle. And this is where the most exciting thing is. This is where you can leverage your creativity and create whatever language that you want, from abstract paintings to something not readable to something plain and simple like expression language. And just to prove you that this whole thing works, so there are like 1, 2, 3, 4, 5, 6, 7, 8, 9 node classes for the Truffle AST representation. There are 3 main classes for the language, the global context, and the types. And then there are 5 until classes, one of which I created myself. So this is basically where I poured my creativity, creating this calculator language. So to prove that it works, let's just run it. I hope it works. It worked in the morning. Don't save. Don't do anything. Be nice to me. What happened? Deselect all. OK. Running. So that was. So now we can do simple expressions. And we can see that when we get the result of the evaluation of the program, we will print out the class of that result and the actual value. So if we do 1 plus 2, we get 3. So let's do something more complicated. Can we do a tree? OK, save it. Don't bother me. So if we do something complicated, we get the result. And that is actually a true arithmetic result. Not very fancy to see how the calculator works. What do you think will happen if I use a different input with 4.0 in the middle? Who thinks that the result will be 10? Who thinks that the result will be something different? OK, who thinks that the result will look different? Yeah, see, this is the correct question. And indeed, the result will look different. It's 10.0, because we now are in the floating point computations, and we're not operating on just longs anymore. And as we specified in the application of the operation nodes, if we have a long and big decimal operand, we will convert them and specify the rules. Now, I have this different example where the .o goes into a different place. What will be the result of that? Who thinks that the result of that will be 10, like 10? Who thinks that the result will be 10.0, like 10.0? Who thinks that the result will be something different? An exception, perhaps? No? Well, surprisingly, the result for this operation is 10 in the scientific notation. I'm not exactly sure why it's happening, but I blame big decimal. Now, this is cool. This is cool. So I have 2 longs, and if you see this value is the max value minus 1. So this is what happens. Longs. So if I run this example and just add those 2 values, who thinks that the result will be long? Who thinks the result will be a big decimal? Yeah, that was kind of easy, right? No, don't select. Oh, OK, select. But not. So indeed, the result is a big decimal, and this is the number that does not fit into a long. And how we got there, we got 2 long operands, and we said, oh, please add those together in this addition node, right? And Truffle figured out that we are dealing with longs, so it went and executed this specialized code for us. And it executed that, it got an overflow, it got an arithmetic exception, and then it bounced back automatically to use a different notation. Well, actually, to this. So they were not big decimals, both of them, and they became big decimals both after that. So Truffle could not execute the optimized code, and it bounced back. And to do that, we did absolutely nothing than to slap this specialization annotation on this kind of small method. So with that, we're going back to slides. Can you see the slides? So our result, what we had, we created a fully functional calculated language. How much out of time am I? OK, I have just one slide. So we created this language that will take the expression string and will create the lexing thing and parser, and then we will compile that with this magical truffle that does a lot of things for us, from type description to running optimized code to providing insights and kind of access to the guts of the JVM. And then the JVM executes that, and we get the result. And to me, that is very fascinating. And you can take it from there anywhere. Just to be kind of cheeky a little bit, Growl actually is very fast virtual machine. So for example, it runs JRuby pretty fast, and it runs R pretty fast, and it runs JavaScript almost as fast as V8 at some point of time in this universe. So the combination is amazing. Truffle is really good for managed language runtime implementation. Growl is amazing to optimizing that. As a language designer, you will just need to specify just a bit of code to express your creativity in the best way. So this is it. If you have any questions, we are sadly out of time, but I will still be here. So ping me, email me, just find me and talk to me. I hope you got fascinated with Truffle, and if you want to develop a programming language, you should try that. It's a very rewarding approach. Thank you.